And then if
it is recording.
Okay, it's recorded. So let me see what we can do. So I will start with sharing. Okay. I hope you can see my screen. And I know that I am not in the mode of presentation. However, I would like to interact with you and also write something on the slides. So let me see what will happen. I will start the presentation. Okay. But at a certain moment, I will need to switch to a different mode. So as I promised you, this will be very, very basic introduction to NMR relaxation and NMR itself, just as a phenomenon. Let me start something with extremely simple. I always hesitate to display this figure because after that, people tend to think that NMR is entirely associated with water. This is actually not this case. However, water is something which is a very nice object to start discussing relaxation and NMR phenomena. So you see here a box. In the box, we have drawings showing several water molecules. Now, okay, let us be, I'm still trying to accept people. Let it be like OH2. Yeah, so each molecule includes 2 hydrogen atoms. As you know very well, atoms consist, okay, still accepting people, of nuclei and electron cloud. This is this very, very simple school definition. Yeah, so in our case, the atoms which are of interest for us are hydrogen atoms. Hydrogen atoms are the simplest one, and the nuclei consist just of 1 proton. And of course, to make the atoms neutral, we have 1 electron. Focusing on the proton. Protons possess magnetic moments. Well, I will not go as far as to high school physics, and I will not explain what magnetic properties are, but if we can just say this in words, well, you remember for sure just magnets from school. You know that you can buy a magnet going to a trip and put it on fridge or somewhere in your laboratory. So in this sense, protons show similar magnetic properties. However, and one can imagine in a very naive way, but I have the feeling that actually we are very limited, all of us, in our senses, and we imagine things just as we can, yeah, and it applies to all of us. So we can imagine that the magnetic moments are just this kind of arcs. And if there is no external magnetic field, those magnetic moments are distributed, their orientations are distributed completely random, as you can see. So if you take a glass of water, using it as example, and you ask yourself what is the effective magnetic moment of all the water molecules in the glass, the answer will be 0. Because, yeah, if one is up, another one is down, so it compensates. If one is to the left, another one is to the right, so it compensates. So water, glass of water, just does not show magnetic properties. In the same way, actually, we also include a lot of water, actually also other hydrogen atoms from other molecules, and as such, we do not show magnetic properties. So this is not surprise. Then this is our side. Let's think in this. Then we put the sample into a magnetic field, external magnetic field. And here I will use big words. Quantum physics and quantum mechanics starts playing a role. You know, this is something which people do not like to hear. However, it's very simple to understand. Look, if there's no quantum physics, in principle, we can take, let me use this example, whatever position we like. Yeah, we can I don't know, we can stay, we can sit, we can, how to say, be in a somewhere position between. Okay, I do not want to talk that this will be quite uncomfortable and how long one can practice some fancy yoga figures. However, in principle, we can do what we want. It is not like that in quantum physics. The principles of quantum physics is that only certain so-called states of the systems are allowed. And other states are just not possible. So if you put your sample into a magnetic field, a surprise, the magnetic moment can take only two possible orientations, parallel and anti-parallel to the magnetic field. Parallel and anti-parallel to the magnetic field. This takes some time for the magnetic moments to reorient, and here is the trick. Because although we need simple pictures to visualize what is going on in the system, the most dangerous thing is start to imagine now that, you know, this sphere somehow as a whole turns and then the magnetic moment is up. This is a very naive picture, and this is not what is happening. Please do not associate the changing in the orientation of the magnetic moments of protons, which are the nuclei of the hydrogen atoms, with changing orientation of a molecule. This is not like that. So this is the first trap if one wants to build, if you want to build in your mind a kind of simple picture of relaxation. And NMR. Forgetting for a while about that, please accept the situation that there are two possible orientations of the magnetic moments and nothing between. You know, then this is now a next. Namely, let me again use some simple analogy. Let's assume that you go to a lecture, and well, the teacher is very popular, and you are very, very much interested in the lecture. I know that I'm drawing a kind of idealistic case. However, the lecture room is small. Well, and there is limited number of seats. Of course, everybody wants to sit. Nobody wants to stay during the lecture. So you will start, how to say, fighting for seats. I mean, do not take it literally, but you would much prefer to sit than stay, and people will decide to stay only if all seats are taken. Then assume another situation. The room is large and there's a lot of seats, but there are better or worse for whatever reason. Yeah. So of course, first the better seats will be taken, whatever it means. However, you will be not so much disappointed and angry if you do not get the better one, So somehow it does not make so much difference to you, like between just sitting and staying. Why I'm saying? Because those two orientations are associated with energy. There's a certain interaction energy between the magnetic moment and the external magnetic field. And the interaction energy is different when they are parallel and different if they are anti-parallel. It does not matter in which case it is smaller. I never remember. It is not important at all. The thing is that in the example which I gave you, translating into quantum physics, it means that we want to occupy the state of the lowest energy. This is a fundamental rule of our world. Our world tends to take minimum energy. So what will happen? Of course, those orientations which are associated with a lower energy will be taken first. And then the ratio between the population of the lower energy state and the population of the higher energy state is described by, again, a fundamental law of nature. It is called Boltzmann distribution. The so-called Boltzmann distribution gives you the probability of a certain energy state being taken at a certain temperature. So of course, the probability is higher for lower energy. Then one can say, now, okay, maybe this is clear, but why I was building this story about sitting, standing, and more comfortable chairs and so on. Because here we have the magnetic field. And as I said, there are those two energy levels. And there is a difference in energy between them. One is lower, one is higher. But now is the story. How large is the difference? Because actually, if the difference is huge, it's like being like between sitting and standing. You care a lot. If the difference is small, like between less and more comfortable chair, so you care less. And the difference in the energy levels is proportional to the magnetic field. So at high magnetic field, the difference is large. At low magnetic field, the difference is small. We have Elizabeth. So what is happening? At high magnetic field, the probability of taking the difference in the probabilities of occupying those two energy levels are much more significant than at lower magnetic. Then what is happening? Let's assume that I have 1,000 magnetic moments in my sample. This is completely non-realistic. And if there will be no preferences, it will be like 500 to 500. However, if I have large magnetic field, please pay attention that the numbers are not representative at all. It's only to give you the idea. I have like 700 for the lower state, 300 for the higher state. So the difference is 400. Yeah. So my system gains microscopic magnetic moment. Let's put it in this way. Or maybe the word macroscopic is not the right. It's a magnetic moment which can be detected in NMR experiments. And the magnetic moment stems from the difference between the populations of the lower and higher energy. Then and this effective magnetic moment is called magnetization. So you know what is happening. Random distributions of magnetic moment, no magnetization. I apply an external magnetic field, and the system tries its best to follow the quantum physics rules. So no, only two orientations are allowed, and the populations of those two energy levels associated with those orientations follow the Boltzmann distribution. But this takes time. To change the state of this system from such one to such one, which corresponds to the equilibrium described by the Boltzmann distribution. So what is happening? The magnetization is zero.
Danuta?
Yes?
Just sorry for interrupting. Are you changing slides?
No, I'm not changing slides so far.
Okay.
Then I will change in a second.
Okay.
I have only 3 slides, by the way. Then I will interact with you. So we have here zero magnetization. Then time is going. Yeah, you have time on the x-axis, and the system just goes through this procedure to reach eventually this equilibrium. So let's say 700 magnetic moments up, 300 down, and nothing will change. And if we do not vary the magnetic field. And generally saying, this tendency to reach equilibrium is called relaxation. And relaxation time merely describes how fast the equilibrium is reached. You will often deal with something which is called relaxation rate. And relaxation rate is just reciprocal relaxation. So now I will try to switch slides, which I hope it works. And let me now make a kind of summary what I said. Hydrogen atom clearly possesses magnetic moments. Yeah, we agree. In a magnetic field, the magnetic moments can take only two orientations: parallel or anti-parallel to the magnetic field. This we also know about. I said that more magnetic moments is oriented parallel than anti-parallel. Yeah, so now I remember which energy level is more popular. The difference leads to an effective large magnetic moment, which is called magnetization. Then, as I said, the reorientation of the magnetic moments requires time. It is called relaxation time. But there is something which is also mentioned here, and I didn't touch the subject yet, is just energy. The orientation of the magnetic moments requires time and energy. Well, why energy in a second? However, here I decided to provide a kind of definition. The time needed for the magnetic moments to reach the distribution of reorientations appropriate for a given magnetic field is called relaxation time. I hope this is clear. Yeah, as I said, it's just the time which the magnetic moments need to reach the state dictated by quantum physics. Then there's a magic. The energy needed for the orientation is taken from molecular motion. Does not matter which one. Okay, we have more people. Look, before I start developing this thing about energy, if I have such a situation, then let's assume such a thing. Maybe it will be better to understand in this. I applied a certain magnetic field, and my system, it can be zero, yeah, in the principle. One can also say that I applied zero magnetic field, but let us not dwell on the limiting cases. So I applied a certain magnetic field, and my system reached equilibrium. Then I increased or decreased the magnetic field. What the system is supposed to do? Let's assume that I decreased the magnetic field. Well, when I decrease the magnetic field, the system should adjust to the new equilibrium. It means the populations of those energy levels should change. At higher magnetic field, the difference was higher. At lower magnetic field, it will be low. So what must happen? Those magnetic moments which somehow were, let's say, one can put it in different ways. One can say that those magnetic moments which were at the higher energy level, which was not convenient for them. No, I should put it differently to make it understand. We have those two energy levels. And as I said with the analogy with the charts, yeah? If this was between sitting and staying, it is like that. Then the magnetic field is lower. The preferences are not so strong. So in principle, those magnetic moments, which very much wanted to occupy the lower energy level, can in principle go to the higher one. Of course, they still do not like it. However, well, the disliking is not so strong. So, expressing this more scientifically, at higher magnetic fields, the probability of the magnetic moment taking the lower energy level is much higher than for the higher energy level. When I reduce the magnetic field, the probabilities will not become equal, but more close to each other. The difference is not so strong. But what does it mean? I said at the beginning, and I keep repeating that those two energy levels are associated with energy. If magnetic moment changes the energy level from the lower one to the higher one, it must take energy from something. If it goes in the opposite direction, it changes its energy level from the higher one to the lower one. It must be something in its surrounding what is ready and willing to accept the excess of energy. Because if the system will be closed, of course, there will be no transition path. Therefore, this procedure of adjusting to the conditions dictated by the magnetic field is not called only relaxation, but also spin lattice relaxation. Why spin lattice? Because all the surrounding molecules form a lattice. It's just a terminology which one might like, one might dislike. A lot of terminology is, we are wondering why it is so and what they stem from. However, I suppose it is quite clear. It's like, in crystals, you have just unit and crystal lattice, the surrounding. So maybe the origin is like that. Namely, all the molecules which are in the vicinity of the atom and this magnetic moment which we are discussing, all the other molecules in the sample form so-called lattice. And this requires energy, as I said, because the energy must be exchanged with the lattice. However, how first, what kind of energy? Second, how it is supposed to be exchanged, Because it's like, a kind of discussion. There are two people, they close to each other, and they say that there is positive energy between them, and they exchange energy. Yeah, but how in principle, if you want to think strictly and you want to know how the procedure takes place, Look now at this, at such situation. I said at the beginning that the magnetic moments interact with external magnetic field. And this is the reason of those two energy levels. However, the magnetic moments interact not only with the external magnetic field, they interact also with each other. Because why not? Yeah. The magnetic moment of the nucleus of one hydrogen atom in water molecule can interact with the magnetic moment of the second hydrogen atom. There will be intramolecular interactions because it's within one molecule. There are also intermolecular interactions with magnetic moments of the nuclei of neighboring molecules. However, what is the nature of the interaction? Well, it's the same interaction between the external magnetic field and the magnetic moment, such as magnetic dipole-dipole interaction, because there are two magnetic dipoles. However, there's a difference now. Namely, those fluctuations, those interactions between the magnetic moments of different nuclei fluctuate stochastically in time. I said already a lot, but this is the principle of relaxation. What does it mean? Stochastically, it means randomly. So they're like that, like that, like that, like that, like that, and there's no sense. Yeah. So they fluctuate random. Why? And why they fluctuate like that? Because molecules move. Imagine, for instance, that you focus your attention on one water molecule and you say, the time is frozen, just like that, stop. So there is this external magnetic field, there is the water molecule, there are those two hydrogen atoms, and you can draw a line connecting those hydrogen atoms. And the line will form certain orientation with respect to the magnetic field. But you know, the molecule rotates. There is such a thing like Brownian motion, which includes rotational and translational diffusion, and it also includes other kinds of motion. But focusing on those two, this molecule rotates. It does not perform a kind of motion like, around the clock, yeah, can't. It fluctuates stochastically the orientation. So it's like that, and there's no sense in that, let's say. The motion is completely stochastic. But then it means that the orientation of the line between those two hydrogen atoms just changes in time stochastic. Then you can say that you have a coupling, magnetic dipole-dipole coupling, between hydrogen atoms belonging to different molecules. Here is even worse, because both those molecules perform translation motion, and they also rotate. So not only the orientation of the axis connecting those two hydrogen atom changes, but also its length, because the molecules can be more close or more far apart. Actually, talking about translation diffusion, please do not mistake translation diffusion in terms of stochastic motion, Brownian motion, with diffusion in a gradient. Because what people usually think is that when one says about diffusion, it's like, okay, let me make this analogy. There is something smelly in one corner of a room, and after some time, yeah, everybody knows that there is something smelly. This is called diffusion in a gradient, because the concentration of the smelly molecules are at the beginning only in one room, in one corner. So there is a gradient in the concentration. In one corner, the concentration is higher, another one lower, at the beginning is zero. Yeah. This is not this kind of translation we are talking about. We are talking about translation, diffusion as a Brownian process. So if you take water molecules, if you take a glass of water, there's the same amount of water in each place of the glass. However, the molecules are not frozen. If you would be able to distinguish between them, and you will name one of the molecules one, and you will like it for whatever reason, you attach a kind of label to it, which is impassible, then the molecule will move stochastically in the glass. And after some time, this particular molecule will take all possible positions in the glass. The same, of course, happens to any other molecule. However, as you cannot distinguish between them, for you, this is like static picture. But no, there's constant movement behind that. So this is meant by translation diffusion. So now, okay, we have a kind of initial equilibrium, initial distribution of the magnetic moments, certain amount up, certain amount down. Then we change the magnetic field, and the system adjusts to the new conditions. It means the population changed, yeah? So the effective magnetization, which is the difference between those two populations, change in time. The changes, as we already concluded, are possible because of magnetic dipole-dipole interactions with surrounding magnetic moments. The relaxation time or the relaxation rate, which describe the effectiveness of the relaxation process, long time, the relaxation process is slow. Short time, the relaxation process is fast. In other words, small relaxation rate, the process is slow. Large relaxation rate, the relaxation process is fast. The effectiveness, the speed, although I do not like this word in connection to relaxation, of the relaxation process depends on the probability per unit time of transitions between the energy levels of those magnetic moments. And the probability depends first on the strength of the interactions between the lattice, so the strength of the magnetic dipole-dipole coupling, which for obvious reason depends on the distance between the interacting magnetic moments as one of the factors. And then depends on the time scale of the motion, how fast the molecules move. And here is something which you should pay attention. Look, this is playing with units, but this is assumption. When I was talking about the two energy levels and the difference between them, what are the units for energy? Joule, for instance, yeah? This is what you probably know from school. The thing is that the difference between those energy levels, which is of course energy itself, can be expressed in frequency. I do not want to go very deeply into physics. However, there is a Planck rule. Yeah, for sure you heard about so-called Planck constant, which more or less says that energy is Planck constant times frequency. Not going into physics, energy can be expressed in frequency, in hertz, kilohertz, megahertz, and so on. So the gap between the two energy levels can be given like, 1 megahertz. Yeah. And then if the energy is expressed in hertz, in frequency units, let's say, you can compare it with the time scale of the motion. So if there's also characteristic time scale of motion, not going again into details. For instance, you heard about diffusion coefficients, which merely, this is a high school problem, which merely says that larger diffusion coefficients means faster motion, and so on. There's a quantity which is called correlation time. It was to a large extent invented for the purpose of nuclear magnetic resonance, but not only. Namely, so-called correlation time gives you information about the time scale of the molecular motion. So coming back to the efficiency of the relaxation, the process is most efficient. It means the exchange of energy between the lattice and the magnetic moment of question is most efficient if the correlation time, so the time scale of the molecular motion, matches the energy gap expressed in frequency units. So 1 over the correlation time, the inverse correlation time, should be of the order of the frequency representing the gap between those two energy levels. Then the transfer of energy is most efficient. You see, this is something about resonance here, yeah? The school definition of resonance, that some frequencies should agree. It was like with a swing. You have to push it with a certain frequency. Otherwise, it does not happen. Then there's a third factor to which will come in the course of the lectures, which is the mechanism of the motion. Surprisingly, it matters if the motion is rotational motion or translational motion or any other kind of motion. Even if they are of very similar time scale, even identical time scales, let's say they have the same correlation time, the mechanism of the motion affects the transition probabilities between those two energies. So there are those factors. And here we reached something very important. Because when we perform relaxation experiment, we look at the relaxation time already. And from that, we want to learn about the molecular motion. So this is the link. This is what I wanted to tell you. The relaxation time or rate, the speed of the relaxation process, the efficiency of the relaxation process depend on the time scale of the motion from which the energy is taken. As it depends also on other factors, like the amplitude of the dipole-dipole interaction, which is determined by the structure of the molecules, as it depends on the mechanism of motion, and NMR relaxation became a very valuable tool to probe dynamics and structure via this way. So here I summarize it a little bit. So as I said, this will be my last slide, and then we'll start building something together. So I will invite you to build a kind of relaxation model together with me, and I will need to switch to a different presentation. But summarizing here, random distribution of magnetic moments. Okay, we apply magnetic field. Well, the system, in this by system I understand now the collection of the magnetic moments, wants to take the state which is required by quantum physics, parallel or antiparallel, and which one with certain probability. But they need energy and time for that. Time is passing anywhere. However, they need energy. So this is what I said. There are magnetic dipole-dipole interactions that stochastically fluctuate on time because of the molecular motion. The magnetic dipole-dipole interaction are the pathways for transferring the energy, like, I don't know, holding hands to give you the courage to pass a test. This is the hand between them, magnetic dipole-dipole interaction. They exchange energy in this way. And the effectiveness of the exchange depends, of course, on the strength of this coupling, depends on the time scale of the motion of those molecules, because the coupling fluctuates in time with this time scale, and depends also on the mechanism of this motion. And this process is going on, and the magnetization evolves in time. In this case, it grows up, but it can also decay. It depends how the condition change until, until equilibrium was reached. So we observe the relaxation process. So this is what I wanted to tell you. I will stop for a while this sharing, and maybe we can do it in a different way. Before I stop sharing and start again, maybe you have any kind of questions. As I said, we can cut it off from the recording or do whatever you like. Do you have questions? Okay, as I do not hear any, let me stop this recording. It is this sharing. Something strange happened. And now I will share again, but in such a way so I will be able to write something. So let me start sharing again. And I am here. However, on purpose, I will not switch to the presentation mode because I would like to interact with you at this moment. And I would like you to participate in building a relaxation model, relaxation schema. So I'm starting. Yeah, so the point one, let us make such a summary that it is clear for you. So what is the first? We need a sample. So let me put it this way. We are taking a sample which includes atoms, the nuclei of which possess a magnetic moment. This is the first thing. You might be surprised. It can be 1H, it can be proton, hydrogen, fluor, carbon, but carbon-30. And many others. But for some reasons, mostly hydrogen and fluorine atoms are mostly preferred. Then, what is the next? In the next can be like that, we apply the magnetic field. What is happening? the magnetic moments orient parallel or anti-parallel to the magnetic field. And here I have surprised. Provided, I will write something that will surprise you, the spin is 1/2. Oh, you see, there is something new here. Because I was talking about magnetic moments, now I'm talking about so-called spins. And in addition, I name a number here, which is supposed to be 1/2. You know, for instance, this magic spin for nitrogen 15 is 1/2, but for nitrogen 14 is 1. What does it mean? The magnetic moment is proportional to a quantity which is called spin. From the perspective of physics, it's nothing else like a characteristic properties of systems, like mass, for instance. If a nucleus possesses a magnetic moment, it also means that it possesses a spin. However, the magnetic moment is proportional to the spin. The spin does not need to be 1/2. It is 1/2. 1/2 is the lowest value of a spin. If you will be reading whatever kind of NMR books, I hope you will at a certain moment, the concept of spin is everywhere. So therefore, I'm telling you about it. Hydrogen atoms, I mean protons, and nucleus of fluorine atoms and carbon-13 and nitrogen 15 possess spin 1/2. Quite surprisingly, the nucleus of nitrogen 14 possess spin 1. It depends on the composition of the nucleus, how many protons and how many neutrons it includes. What does it mean if there's, for instance, spin 1? Look, this implies its behavior in the external magnetic field. As I didn't say it at the beginning, talking about the parallel and anti-parallel orientation, that it concerns only nuclei of spin 1/2. But if it is 1/2, it's like that, or like this, you know all. What happens if there is spin 1? Like that, and like that. There are 3 possible orientations in the magnetic field. They can be higher spin, even 9/2 some would say. Then you have a variable, a load orientation, like that, like that, like that, like that, like that, like that, like that. Sure. However, not going to high spin quantum, for high spin, to high spin numbers, it is worth to know at this stage that actually nitrogen 14 has spin 1, because nitrogen 14 is quite often present in biomolecules, and there will be several effects associated with it. Otherwise, more orientations can be taken. For instance, 3 for spin 1, like for nitrogen 14. Yeah? So we learned some. Let us go to the next. It's nice to have it in such a way. So let us proceed further. the magnetic moment is proportional to the speed, but not only. It is also proportional to the so-called gyromagnetic ratio. In other words, fact. Well, this is a nucleus specific value. So each nucleus, like hydrogen atoms, nuclei means protons, have certain geomagnetic factor. Fluorine nuclei have another geomagnetic factor, and so on and so on. Why I'm saying? Because this is also a quantity which will be everywhere. So let us continue this stuff. Yeah, next bullet point. The gyromagnetic factor is an extremely important quantity. Why? For two reasons. First, it determines the strength, in other words, amplitude of dipole interactions. So the first reason is that it determines the amplitude of the dipole-dipole interactions between different magnetic moments. Larger geomagnetic factor means stronger interactions. But it's another, which is maybe even more important, although it's hard to say what are important. It determines the strength, amplitude, of the coupling between the magnetic moment and the external magnetic field. Because as I told you, this is something very similar. So geomagnetic factor is really crucial, and I will show you some examples of geomagnetic factors, but you should know at this moment that geomagnetic factor, hydrogen atoms, protons, possess the largest geomagnetic factor. So then there is a next consequence. As it determines the strength and, in other words, the amplitude of the coupling between the magnetic moment and the external magnetic field, one can say that consequently, the geomagnetic factor determines the energy, the values of the energy levels And consequently, the value of the energy gap, in other words, difference, let me make it, between those energy levels. I will make here significant assumption for a given magnetic field. What I have in mind, let me read it again. Consequently, the geomagnetic factor determines the values of the energy levels and hence the value of the energy gap, the energy difference between those energy levels for a given magnetic field. What does it mean? We use the same magnetic field. Higher geomagnetic factor the same magnetic field and the same spin. Like, for instance, 1H and carbon 30. Higher geomagnetic factor means a higher geomagnetic factor means a higher energy gap. This makes sense. So let us continue the story. Yeah, we can, in principle, continue our story. You will have nice view, and then I hope we'll fill it in together. Therefore, I'm writing this with you. So we finished stating that different geomagnetic factors determines the values of the energy. The geomagnetic factors determine the value of the energy levels, and as a consequence, the value of the gap between those energy levels. And for a given magnetic field, use the same magnetic field, and you have the same spin, like for instance, 1/2. Both those nuclei have spin 1/2. Higher geomagnetic factor means a higher energy. And here I will write something which I will put in red. The energy gap difference between the available energy levels. Yeah, one can put it in this way. Expressed in frequency units is called resonance frequency. This is what should be put in red, made very, very large, and never forgot. Because you will hear very often about resonance frequency. So now I will have a question to you. Let me put it in this way. Yeah. So let us continue. I will put it in this way. The life-changing conclusion. Of course, you know, did this with a kind of distance. However, what does it mean? What I mean here, what stems from that, the discussion about the geomagnetic factor and the statement that the energy gap expressed in frequency units is called resonance frequency. The energy gap is proportional to the magnetic field. Yeah, to the applied magnetic field. This means that the resonance frequency is proportional to the magnetic field. Yeah, because the resonance, the energy gap in frequency units is nothing else like the resonance frequency. So the energy gap is proportional to the applied magnetic field. The resonance frequency is proportional to the magnetic field because energy gap and the resonance frequency means the same. It's only the matter of units. This brings us to next conclusion. Because when we have here, we stated that the geomagnetic factor determines the values of the energy left. So it brings us to the conclusion. The resonance frequency, Control C, Control, well, that's not. Sorry. The resonance frequency is given as the product of the, may be different, is proportional to the product, to a product of the magnetic field and the geomagnetic factor. Yeah. This means that for a given magnetic field, the resonance frequency depends on the geomagnetic factor. So let me save that to share later with you. I will stop sharing for a while and then I will show you something. Let me now go to Wikipedia. Okay, I have it here, so I will start sharing again. look what you have here. This is just Wikipedia geomagnetic ratio. Here is heavy physics behind, it does not matter. What is important for you is that you have here a list of nuclei which possess magnetic moments. This is not the exhaustive list, but you have some of them. They have different spins, let's say. And here you have geomagnetic factor. It can be in different units. It can be in, here for instance, in megahertz per Tesla. And it's like 32.6. What does it mean? If I take hydrogen atoms and I apply magnetic field of 1 Tesla, then the resonance frequency, the gap between those two energy levels expressed in frequency units, will be 42.5 megahertz. So in relaxation, in NMR, not only in relaxation experiments, although we are focused on relaxation, as I think what very often you will hear about, resonance frequency is something extremely basic. However, you will have performing relaxation experiments at 20 megahertz, or in the frequency range from 10 kilohertz to 10 megahertz, or performing experiments at high magnetic fields, like, 600 megahertz. The first question is, for which nucleus it has been performed? Most typically, it would be for hydrogen. Then you know what magnetic field was applied. This is just the direct proportionality between magnetic field and hydrogen atoms, and the resonance frequency for hydrogen atoms. Here, look, this is 42.5. I look at fluor, another quite often present nucleus. It's 40. So you see, here is the largest value. Here is the second large. They are, how to say, the most prominent nuclei for nuclear magnetic resonance. If you compare, for instance, with nitrogen, you see it's like 10 times lower. Does not matter the sign at this moment. So this is what it's worth to look at. Let me stop sharing. And then I will start sharing again, however, going to my favorite presentation. And I would like to ask you at this stage whether you have any questions to. If not, I will have questions to you. I will be typing them on chat, and then we'll see whether somebody will answer to me. If not, I will try to answer myself, but I would prefer that you give me the answer. But let us wait for a couple of minutes. Not much, just 3 minutes, okay? So you have time to gather thoughts, whether you have any questions. If not, then we'll have 20 minutes to play our game. Oh, I can finish copying it. It's cold actually. I will finish the copy. We'll wait 2 minutes. Then I will appear on the YouTube, but I didn't write my copy. So giving lectures online is kind of scary thing. Yeah. There are no questions. So, okay.
No.
So if there are no questions, let me post a question and I will see whether I will get from you any kind of answer. I hope I will. Otherwise, I will answer by myself. What magnetization stems from? Is magnetic field needed to get a magnetization? So it's my first question. What, of course, not what magnetization stems from? Is magnetic field needed to get a magnetization? Somebody is saying that yes, yeah? Yes, magnetic field is needed to get magnetization for this reason that only in the magnetic field, the magnetic moments of individual nuclei are put in a kind of order. So they take only the allowed by quantum physics orientations, and therefore, as a difference between the populations of the energy levels associated with different orientations, we get the magnetization. If there is no magnetic field, the magnetic moments are distributed completely randomly and they compensate. So there is no magnetization. Do we need molecular motion to observe? This is tricky, to observe relaxation processes. Observe, I have some trouble. I write too fast. So do we need molecular motion to observe relaxation processes? The answer is no. This is what Carol said. Are there any different opinions? Yes, we need. This is what Adriana says. So we have like 1-1. So what are the next opinions? Because we must take a decision. One person says yes, one person says no. Adriana says that also the temperature must be different from 0 Kelvin, which makes a kind of sense because if the temperature is 0 Kelvin, there is no motion. So yeah, Muhammad says yes. So Carol, it seems more people think that yes than no. Let us wait for one more answer. It's starting to be fun. There's no more. Kahinga, yes, we need, sure. First, if we do not need motion, even on a very, very basic level, as relaxation is meant as a tool to study molecular motion. So even if we do not know what motion has to do with relaxation, the answer will be obviously yes. Because if, as I said, NMR relaxation is meant to study motion, yeah? So the processes must be connected. However, now, how they are connected? You know, when I started this lecture today, I just thought that it might be too simple and somehow, well, that I should have hundreds of nice slides, but I do not, because actually on purpose, because then I will give one more lecture and will say, yeah, let us have coffee break. And I think it is better just to interact with each other. And I think that this situation really proves. The answer is yes. As I said at the beginning, you know, to switch again to the relaxation, to the presentation mode will mean stop sharing, which I do not want to do, because then I will need to start sharing again. We agreed. Muhammad wants me to extend second point on fifth slide. I will do it in a second, sure. However, answering to the question about the molecular motion. Relaxation means adjusting to the equilibrium. So as I said, we're focusing on two energy levels. If I change the magnetic field, the populations of those energy levels also must change to adjust to the equilibrium. So it means magnetic moments which were oriented like that must be oriented like that, or another way around. Some of them which are oriented like that must be now oriented like that. If you are changing the energy level, it requires energy, yeah? After all, it's something very simple. If you are, how to say, sorry for that, it sounds, but maybe in this way you'll remember. Let's assume that somebody has a heavy flu. After some days, the person is exhausted. The person does not eat much, drink something, yeah, and generally. So the person will say, oh my God, I'm lying in bed. I do not have the energy to leave the bed. It means to sit or to stand up. You literally use this word like in everyday language. Because going to a higher energy level, it means, yeah, taking energy from something. In this way, you can also assume that, I mean, believe it's also obvious that to going to a lower energy level, you have to release the energy, yeah? After all, I don't know, locomotive in the old trains or something like that. So you exchange energy. You exchange energy with the lattice, and the energy is taken from the movement in this sense that the dipole-dipole coupling provides the link here. And the dipole-dipole coupling fluctuates in time because of molecular motion. And the effectiveness, the efficiency of the relaxation process depends, as I said, on the amplitude of the coupling, on the time scale of the motion, and on the mechanism of the motion. If there is no motion, the system is frozen. The coupling does not fluctuate in time. And we need the fluctuations to cause the transitions between those energy levels. Motion is essential for relaxation. No motion, no relaxation, never ever. Is the basic principle of nature. You must have interaction fluctuating in time to cause transitions between energy levels. And those of you who are a little bit familiar with relaxation, for instance, Carol, take the simplest expression, which I didn't want to use at this moment because I wanted to do it without mathematics. If you have the expression for relaxation rate in terms of the Lorentzian spectral density, no motion means infinitely long correlation time. There's no motion. The relaxation rate will be zero. There will be no relaxation. Just motion is the principle, the essential fundament, the very, very basic effect which causes relaxation. And therefore we can profit from that. Can you explain second point of 5 slide? We apply a magnetic moment. We apply a magnetic field. This is, I think, clear. The magnetic moments orient parallel or anti-parallel to the magnetic field, provides the spin is 1/2. Sorry, because I was doing this. Otherwise, more orientations can be taken. For instance, 3 orientations for spin 1. What I have in mind. If we have spin 1/2, like for hydrogen atoms or fluorine atoms, for magnetic moments associated with spin 1/2, take in external magnetic field 2 orientations. Parallel, which means the angle between the magnetic moment and the external magnetic field is 0, or anti-parallel to the magnetic field, which means the angle is 180 or pi, depending on the unit used. And there are only 2 orientations. If I have spin 1, like for instance for nitrogen 14, there are 3 passive orientations. Parallel, which means the angle is 0. Perpendicular, which means the angle is 90 degrees or pi, anti-parallel, which means the angle is 180 or pi. If you have even more higher spin quantum numbers, it's just the concept of so-called magnetic quantum numbers. You know, that you have then many more orientations. It's like you have this the spin quantum number, which is like 1/2, 1, 3/2, 2, 5/2, 3, and so on, up to 9/2. It depends on the compositions of the nuclei. And then with each spin quantum numbers, there are associated magnetic, so-called magnetic quantum numbers. They change from the main quantum number to minus the main quantum number with the interval 1. So for instance, if I have the spin quantum number 1/2, the magnetic quantum numbers, so-called, are 1/2 or minus 1/2. If I have spin 1, the magnetic quantum numbers are 1, 0, minus 1. If I have spin 3/2, I have 3/2, 1/2, minus 1/2, minus 3/2, and so on. Mohammed, is this clear? I hope so. Okay, thank you. So let me, maybe there's more questions. Because we are approaching that. Okay, so I will have question. I applied a magnetic field of 1 type. in which case the resonance frequency will be higher for 1H or carbon 30. Will the result change if I applied a magnetic field of 10 Tesla? So it's like calculating, but not really calculating. I'm waiting for answers. We have like 5 minutes. You look at the agenda. Nobody wants to answer to my questions, but I will still wait. With the results, of course. Oh, I got that. Actually, the geomagnetic ratio. Yes, Mohammed and Carol. Yeah, the geomagnetic ratio for carbon is lower, so the resonance frequency will be lower than for hydrogen atoms. However, it's not 4 times, but 10 times lower, but whatever. I mean, it does not matter. Yeah, you are not the table of geomagnetic factors. What is important that we know that it is low. Yeah. Will the results change at higher magnetic field? I don't think so, because the proportionality will always hold. Do we have more questions? If not, I propose that we'll take a cup of coffee and we'll make a break, because what we are going to do next, we are hesitating whether the next part will be attractive to you, but we are going to do a simplest math. The thing is that, and please do not get upset because my intention is completely different. We really want to explain things. If somebody, and I suppose we have many people like that, does PhD, for instance, from food technology or something like that, the math which is needed for NMR relaxometry, for NMR relaxation, is, I suppose, like a memory from the first years of studies. Just to make your life easier, as I keep repeating, they know nothing about food, so please do not take any offense. We are just represent really different specialties. So we just thought that if we put together some mathematical things, a kind of toolkit, it will be easier for you to find some rules and just deal with data analysis. So after a break, Adam from my group will be giving a kind of math tutorial. And then we'll see, then we can solve some further examples on the basis of the tutorial. So I will stop the sharing. And let us take a cup of coffee or whatever, and then we'll continue quarter past 11. Okay? Okay, so let us see each other in about half an hour.
Does anyone know with him? No, no, but he's good. He's probably coming back. I don't know. Yes, so he's back. Let's go. I guess. Hello, hello, Jack. What? Wait, what message? Hi. What it is, Magdan, happy birthday to you. Good luck in it. Good, you know, for the birthday to him. I hope I said the nickname right. Thank you. All 1 HP. Jet 1 HP also. Kevin. Kevin.